Okay, so in this lecture, we are going to implement the trend following strategy in code. This lecture is going to walk you through a prepared Colab notebook, although a very good exercise, which I always recommend, is once you know how this is done, to try and recreate it yourself with as few references as possible. As always, you can check the lectures, how to code by yourself, and how to practice for a more in-depth discussion. If there's anything in this lecture you didn't understand, or you think I missed a step, or didn't explain why we were doing something, please use the Q&A to inquire. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. Let's start by downloading the SPY CSV. Since this strategy uses only the historical prices of the asset under consideration, all we need is just a single time series of close prices. Next, we're going to import pandas, numpy, and matplotlib. Next, we're going to use pd.readcsv to read in our CSV. Next, we're going to call df.head to remind ourselves what is inside our data frame. In the next block, we're going to find the log of the close prices and then take the difference to get the log returns. Next, we're going to do a df.head again to remind ourselves that when we calculate the return, the first value is missing. Next, we're going to shift the log returns backwards so that the rows line up with the buy and sell commands that we will create later. Note that this will get rid of the missing value that we just saw. So if we do a df.head again, we can see that the first value is no longer missing, and everything has been shifted down. This does mean, however, that the last value is now missing. Next, we're going to calculate the rolling mean with sample size 30 and sample size 10. Now you might ask, how did I choose these numbers? The answer is, currently we are just looking at a random set of numbers. Later in this lecture, we will try to choose these values intelligently. Next, we're going to plot the close price along with the moving averages. As you can see, it's not easy to tell where the crossover points are, since there are too many data points. In the next block, we'll limit the plot to just the first 300 points. Try to look at this and guess where the algorithm will decide to buy and sell. Next, we're going to calculate where the fast SMA is larger than the slow SMA. Using the np.where function, this will return a 1 where the argument is true and 0 otherwise. Conceptually, you can think of this as like a vectorized if statement. Next, I'm going to print out a portion of the data frame as it currently exists. Obviously, I chose these points because they have a mixture of 1s and 0s under the signal column. So check these out for yourself and make sure that it's doing what we think it's doing. That is, when fast SMA is greater than slow SMA, we should have a 1, and if it's not, then we should have a 0. Next, we're going to shift the signal column forwards so that we can look at the previous signal on the same row. That makes the next lines easier, where we determine where to buy and sell. Recall that we want to buy when the fast SMA overtakes the slow SMA. In other words, the fast SMA was previously less than the slow SMA, and it became greater. The opposite is true when we want to sell. Okay, so look at this code and confirm to yourself that it does what I've just described. Next, I'm going to print out the same portion of our data frame that we were looking at previously. Recall that the signal went from 1 to 0. This means that fast SMA was greater than slow SMA, and then it became less than slow SMA. This means that fast SMA was greater than slow SMA, and then it became less than slow SMA. Therefore, we should find a sell command here. And in fact, that's exactly what we find. Next, we're going to write a function that will determine, for each step, whether or not we are invested. We'll start by initializing a global variable, isInvested, to false. Next, we're going to write a function that will be called on each row of the data frame using the pandas apply function. So this function takes in one argument, which is the row of a data frame. This is why we need a global variable. Since we can only look at one row at a time, it's an easy way to keep track of the state of being invested or not invested. Inside the function, we declare isInvested as a global variable so that we can modify it within the function. Next, we check the various cases where we need to reassign isInvested. If we are already invested and the command is to sell, then isInvested becomes false. If we are not invested and the command is to buy, then isInvested becomes true. Otherwise, isInvested does not change, and it remains whatever it is. This function returns isInvested, which means that when we call df.apply, this will return a pandas series containing booleans. Next, we call df.apply, passing in the function we just created. We assign the result to a new column called isInvested. Next, we calculate the return of our algorithm by multiplying the isInvested column by the log return column. Next, we calculate the cumulative log return of our algorithm by calling the sum function on the algo return column. We get about 30%, which seems good. But let's check the buy and hold return. This just means that we invested on day 1 and never sold. Therefore, the cumulative log return is just the sum of the log return column. When we do this, we see that the result is 78%. Therefore, the trend following strategy performs worse than simply buying and holding. Next, let's calculate the standard deviation and Sharpe ratio of our algorithm's returns. We'll assume that the risk-free rate is 0 for simplicity. Okay, so we get about 0.006 and 0.02. Next, let's do the same for the buy and hold strategy, which is just the log return column. Okay, so we get about 0.009 and 0.0366. So although our algorithm has lower risk, it also has a lower Sharpe ratio. Compared to buy and hold is superior.